In earthquake seismology, several methodologies are employed to study and analyze seismic events. Here are some of the most important methodologies used in the field. Seismic monitoring. Seismic monitoring involves the deployment of a network of seismometers to record ground motion and detect earthquakes. This methodology allows for the real-time detection, location, and characterization of seismic events. Continuous monitoring provides essential data for earthquake early warning systems, rapid response, and seismicity studies. Seismic waveform analysis. Seismic waveform analysis focuses on studying the characteristics of recorded ground motion waveforms from earthquakes. This methodology involves analyzing waveforms to determine earthquake source parameters such as focal mechanisms, moment magnitudes, and rupture processes. It provides insight into the geometry, dynamics, and energy release of earthquakes. Seismic tomography. Seismic tomography is a technique used to create three-dimensional images of the subsurface by analyzing seismic wave velocities. This methodology utilizes seismic waves recorded at various stations to infer subsurface structures and variations in seismic velocities. It helps identify faults, magma chambers, and other geological features, helping in understanding of tectonic processes and earthquake sources. Seismic hazard assessment. Seismic hazard assessment aims to quantify the potential occurrence and impact of future earthquakes in a specific region. This methodology combines historical earthquake data, geological studies, and seismological information to estimate earthquake probabilities, ground shaking intensities, and associated risk. It helps inform building codes, land use planning, and emergency preparation. Earthquake source modeling. Earthquake source modeling involves constructing mathematical models that simulate the rupture processes and dynamics of earthquakes. This methodology aims to reproduce observed seismic waveforms and other geophysical data to understand earthquake sources and ground motion generation. It helps estimate parameters such as slip distribution, rupture velocity, and stress changes, enhancing our understanding of earthquake behavior. Ground motion analysis. Ground motion analysis focuses on characterizing the shaking of the Earth surface caused by earthquakes. This methodology involves analyzing parameters such as peak ground acceleration, peak ground velocity, and spectral acceleration to assess the seismic hazard to structures and infrastructure. It informs building design codes and engineering practice to ensure resilience against earthquakes-induced ground motions. Seismic imaging. Seismic imaging techniques aim to explain subsurface structures and properties using seismic wave. This methodology includes methods such as reflection seismology, which uses controlled seismic source and receiver to image subsurface layers and boundaries, and refraction seismology, which analyzes the bending of seismic waves to infer subsurface velocity variations. Seismic imaging helps identify geological structure and potential earthquake sources. Seismic array analysis. Seismic array analysis utilizes array of closely spaced seismometers to improve the resolution and accuracy of seismic measurements. This methodology enables the extraction of additional information from seismic wave fields, including detailed characterization of earthquake sources, identification of seismic phases, and detection of seismic signals from nuclear explosions or volcanic activity. Seismicity and statistical analysis. Seismicity and statistical analysis involve the study of earthquake catalogs and statistical properties of seismic events. This methodology includes analyzing earthquake occurrence pattern, seismic clustering, p-value estimation, and other assessment of earthquake predictability. It helps identify regions of increased seismic activity, potential seismic gap, and provide insights into the underlying processes governing earthquakes occurrence.